As a participant of any research project which deals with data, we have certain obligations around them and their impact on the research community and beyond. So we felt it was necessary to incorporate such a topic in our webinar series, which supports not only our partnership and our sister projects who have already expressed their interest in this topic, but also any of you who produce or hold data sets, and in particular of atmospheric content and in situ measurement. Okay. Could you please mute your microphone because there is some noise? So CiROCCO provides capacity development activities during its whole lifespan, and especially onwards when the pilots will be gradually implemented and we want them sustained. And I have the pleasure to lead this task. This is the second webinar, which aims, as I said, at enhancing our capacity for data management. The first one dealt with the health impacts of dust and was a raise awareness activity. And as you have noticed, this event is now recorded so that you can view it later on and also disseminate it to anyone you think it might support. And the same goes for the first one and for all of our webinars in the future. And you can find them in the link we provide on top, and you will see them as you see them in this print screen. So, having a quick view on the agenda, first our project manager, Chrysoula, will have 5 minutes to explain what CiROCCO is. What I should now say, and then Orestes will elaborate on, is that CiROCCO is certainly a EuroGEO project. So it is a project that pursues the goals and meets the objectives of the European Group of Earth Observations. And our institute hosts the Greek GEO office, so our connection with the GEO researcher and stakeholder community is year-long, and Orestes has expertise and experience to discuss about the in-situ component of Earth observations. And then we are going practical. Babis has added value to an already established GEO tool to manipulate solar data, the LibInSitu tool, so that it can now process and output air quality in situ data, steps closer to fairness. So please note down any questions or put them in the chat, and we can discuss them in the last part of the meeting. I invite here now Chrysoula to give us a flavor about what CiROCCO is.
Thanks, Eleni. Hello from my side. I'm Chrysoula Papathanasiou. I'm a senior researcher in the Institute of Communication and Computer Systems, and I'm the project manager of CiROCCO. So in very brief, what we are doing in CiROCCO, the vision of the project is to establish an integrated system that will be composed of a network of different sensing nodes, low-cost sensing nodes, higher quality mid-cost sensing nodes, and datasets, satellite observation datasets. We will use data fusion, state-of-the-art data fusion techniques to fuse information coming from low-cost and high-end sensors and in situ and Earth observation remote sensing data. And the aim is to enhance the undersampled areas, the monitoring of undersampled areas, desert areas. This is where we focus on. In this project, we have 12 partners collaborating, coming from 7 countries. The project is coordinated by ICCS, and the technical coordinator is NOAA. We also have CEDARE, is an institute in Egypt, University of Cyprus, CICIC, an organization in Spain, EBOS, again in Cyprus, an SME, Astrocast, and SME in Switzerland, Innocence in Serbia, industrial partner, Intra, and 3 public organizations, a municipality in Cyprus, the Ministry of Labor in Cyprus, and Visium in Serbia again. So in brief, the objectives is the installation and operation of in-situ, low-cost, standalone and electronic sensing nodes, the establishment of a network that will include low-cost and sustainable solutions to monitor undersampled areas, the development of data processing services, the enhancement of climate change models using datasets coming from these sources, integration and assimilation of cross-Copernicus ecosystem, and eventually the acceleration of the adoption of CiROCCO solutions by the wider community. Here you can see in an image the basic components, the core components of the project. So we have a mix of low cost and higher cost sensors in situ, and also, as I mentioned before, datasets coming from satellites, and we foresee data fusion services to concerning data between AO and in situ sensors, and also data fusion services between high and low cost sensors. In terms of communication, wireless and satellite communications are foreseen to ensure data collection, and all these datasets will serve the needs of 4 different services, each one related with one of our 4 pilots: air quality early warning system for human health in Cyprus, renewable energy systems planning in Egypt, land use and ecosystem management in Serbia, and modeling of greenhouse gases and particles emission, our 4th pilot in Spain. In very brief again, the main expected outcomes is the installation of sensors in 3 desert regions operating for a period of at least 10 months. Overall, the coverage of 2,000 square kilometers with 69 stations monitoring 10 parameters for a period of at least 10 months. We aim to achieve our low-cost sensing system to reach a cost of 60% lower price than the current market, validation of datasets, all these datasets in our 4 pilots, improvement of accuracy in the developed models and maps by 10% using in-situ datasets, and collaboration with at least 5 working groups of GEO, Copernicus, and ESA. And here you can see just the distribution and geographic distribution of our 4 pilots in Egypt, Cyprus, Serbia, and Spain. So that was in very brief a presentation of what we do in our project. Hope you got a capture, a flavor, as Eleni said. And you can find further information on our site, and we can move forward with the other presentations. So
Thank you very much, Hansula.
thank you.
So now we will learn some things about how CiROCCO meets GEO and EuroGEO when it comes to in-situ EO, and why this is a win-win connection. And I should say also that together with us is connected the director of the Greek GEO office, Evangelos Gerasopoulos, and also Lionel Menard, who is connected from Paris, and he's also deeply involved in EuroGEO and GEO, and actually has supported and provided the lib in situ towards what we will see in the end, a tool that can be useful for air quality data as well. So Orestis, now you can start.
And we have the additional pleasure of also having Kalamkas from the GEO Secretariat. So we have both GEO and EuroGEO with us here today. So let me share my screen. So I would like to give an introduction on what GEO is, what the European counterpart EuroGEO is. I'm wearing 2 hats today. The NOAA hat that organizes, that is a partner of CiROCCO, but also the Greek GEO office hat. The Greek GEO office has been one of the founding members of GEO, let's say, so we have been doing this for many, many years. We really believe in the GEO initiative, and hopefully we will entice you a bit today to learn more about it. So, GEO, we just had our 20th anniversary. It's a global partnership with more than 115 member governments and 160 organizations ranging from private sector to UN bodies, etc. It has a UN-like structure with a lot of groups and subgroups. Of particular interest is the in-situ subgroup. here is a URL. In general, my presentation has a lot of URLs, so when we share this information later, you can peruse at your own leisure. GEO offers a global platform for scientists to share knowledge. It tries to coordinate a lot of Earth observation efforts for the whole of the planet. And now we are entering our third decade. So the first decade, 2005 to 2015, it was all about finding data and putting data, making data available, acquiring data, etc. So data for all. Our second decade that just ended was services for all. So, okay, use this data to create services. You know the drill from Horizon projects. You know the idea behind. It was all about better coordination the second decade. So the regional GEOs came to be. EuroGEO is one of these regional GEOs. And we also started engaging with global priorities such as the SDGs, UN Habitat, the Paris Agreement, and so on and so forth. Now, in our third decade, we are entering the Earth intelligence paradigm. This is a word with many components within. So basically, we want these services to be approachable by all. We want to curate these services for a host of users. We want to be inclusive, cooperative, equitable, and you shall see, and we have codified this in the new post-2025 strategy that is for the next 10 years of GEO. GEO has a branding problem, because when you think of Earth observation, you immediately think of satellites. We should have put this in the Mentimeter probably, but GEO is not only about satellites. Okay, so on the left-hand side, you can see the Earth observation, the whole value chain. With very small letters, you can see in the left hand, in top left corner, that in situ measurements also come into play. And for the past at least 5 years, but this goes back to the Canberra Declaration, GEO has increasingly acknowledged the in situ value per se. This has been well documented in key documents such as the GEO strategy, the implementation plan, which was recently endorsed, and the GEO work program that will be valid for the next 5 years. As highlights, you can see that Earth intelligence necessitates combination of remotely sensed data with in-situ data, as well as socioeconomic data, in order to have improved understanding, better intelligence as a whole. We understand that EO infrastructure is very expensive. This is not only relevant for satellites, but also for in-situ networks. So sustainability is always an issue, setting up new networks as well. So we want these investments to be driven by user requirements. And we also want the GEO Knowledge Hub. I will explain in a later slide what this is to signpost and support better access to in-situ data. More in particular, now we also have an in-situ data strategy. This is to be approved, of course, but this is almost done. In orange, you can see challenges. I'm sure that CiROCCO and the sister projects and whoever is listening here today, from what I saw back in the Mentimeter, has these challenges. The data is fragmented. You have great heterogeneity, different kind of sensors, different kind of variables, different kind of problems in real-world conditions. You have gaps. I remember the WMO image of the whole Earth, and you have big black chunks of underrepresented areas. You have reuse problems, access protocols, inadequate metadata, and so on. The in-situ strategy is very optimistic. It sets very aspirational, let's say, objectives. We want to advocate for FAIR, see how we can overcome FAIR barriers, understand, quantify user requirements, improve data sparse regions, and incorporate new data sources. So this is very CiROCCO and sister projects. And as well, demonstrate the in-situ value through integration with remote sensing data and socioeconomic for improved Earth intelligence. Okay, this was the global part. We also have the European contribution to GEO. It's called EuroGEO. This is a very rich ecosystem. On the left-hand side, you can see we have DGs, we have executive agencies, you have Copernicus trusted entities, the EuroGEO action groups, research infrastructures, and of course, Horizon projects. So in the middle, you can see two very bad pictures I took in the recent GEO Global Forum in Rome. These are Earth observation related projects, and I see many of the sister projects within, and hopefully you know some of these logos. So NOAA, we really believe in this initiative, and we are very happy that EuroGEO has put in situ is one of the new focus areas, let's say, also of EuroGEO, not only of GEO, with services, including integration of in-situ data, so combining Earth observation with in-situ. We are looking at challenges regarding data usability and licensing, as well as capacity building. So, for example, this webinar today is part of capacity building, and we will be putting this webinar in our contribution to EuroGEO, just to make it a bit more clear how the whole thing works. A small disclaimer, CiROCCO also has explicit GEO-related KPIs, so we need to put stuff in the GEOS portal, and we also have to make a solid connection with Copernicus and ESA products. Okay, I acknowledge that all this may seem a bit complicated, but the good news is that there are multiple entry points to start engaging with this world. And we want you to be engaging with us, because a single bracelet does not jingle, as was one of the mottos from the GEO Global Forum. So, existing tools for mainstreaming in situ in GEO. First of all, we have the GEOS portal. This is a potential user may find and connect with a data provider, including an in-situ data provider. The core of this system is the data access broker, and this basically works with data catalogs. This means that you don't put stuff directly in the GEOS portal, but you go through a catalog, and in the yellow pages you can see existing providers, so hopefully you can see yourself as a potential provider. The GEO Knowledge Hub, this is being maintained by the GEO Secretariat. It's an open source digital repository. It's a way to bundle up research and knowledge. It has an Inverio RDM behind, under the hood. It's very Zenodo-like. But the key, the defining attribute of the GEO Knowledge Hub is the knowledge package. So this means that we bundle things. We just don't put one dataset inside the GEO Knowledge Hub. We make it into a package. So a package may contain, for example, a dataset, software that produces dataset, a publication, or even better, a user story, how this dataset was used by a particular stakeholder. It's good that we have Lionel and Kalamkas today with us, because these are the EuroGEO and GEO Secretariat focal points for a research project, because it's not only about GEO work program activities, but also directly Horizon projects are contributing to the GEO Knowledge Hub. On the right-hand side, you can see potential projects. This is September 2024 status. Perhaps Lionel can give us an update on how we stand with Horizon projects. Okay, I've talked also about user requirements and quantification of user requirements. So here you have two very well-structured databases. On the left-hand side is the Copernicus in-situ component information system. It's quite a mouthful. So this is maintained by EEA. What this database does, it connects directly a Copernicus product out of the 900 or whatever products that Copernicus have with it documents the requirements for this, frequency, level of accuracy, etc. And it also links to the actual in-situ data provider that provides this dataset to Copernicus. And in the background, this is all worked towards creating a Copernicus product. So the left is for Copernicus. On the right, you have the GREX database tool. This again is a well-structured methodology to collect requirements for in-situ data. Initially, this has been created for GEO work program activities, but this is clearly scalable to other types of products. It aims to stimulate dialogue between user and provider, detect gaps. If many users say, I need this kind of in-situ data and this data does not exist, this is a gap. And in this way, it also quantifies the value of in-situ. And hopefully, it enables matchmaking. linking together potential user with a data provider. And very briefly, regarding fairness, this is the GEO, let's say, approach on fairness. On the left-hand side, these are stuff you can find within the GEO Knowledge Hub, are the revised GEO data management principles. These are, let's say, a maximalistic version of FAIR. You have the best practices regarding data licensing guide, what GEO considers a good data licensing for your products and outcomes of from your projects, I mean. And you also have a self-assessment tool for FAIR compliance. This was implemented between the EuroGEO Secretariat and the GEO Secretariat. So we have both people with us here today. If these are entry points still seem too complicated, you also have the EuroGEO action groups to knock on their door and understand what this is all about. There is not a super formal way to enter this. From my experience, once you start working with an action group, with putting stuff in the GEO Knowledge Hub, with working with the in-situ subgroup, you make your own path into the GEO world. And this is my last slide. I stole everything here from Lionel Menard's presentation in the recent GEO forum. These bullets, I mean. In origin, again, the problem. This is typical challenges for an in-situ data creator and provider. We are drowning in Excel files. Metadata leaves a lot to be desired, let's say. It is difficult to scale. The performance may be low and error prone. And there's a beautiful green color. What if data could be self-described? These are questions, ideal questions set by Lionel, but we think that lib in situ can really work towards this direction. What would happen if you could slice, query, and visualize on the fly your data? Save speed on input and output. Make your data more trustworthy for an outsider. Make them more compatible for integration with Earth observation, but with all the other data sets as well. Make them ready or improve their readiness for AI integration and even improve their semantic search potential. So this is the pass to my colleague Babis, that hopefully in his very practical presentation will explain how we as CiROCCO try to tick these bullets, utilizing and expanding on the lib in situ tool. Thank you very much.
Thank you, Orestis. So let's assume that we already have, or we will soon have, our DAST or other in-situ data sets from our 4 pilot areas or from any other area. How to manage this data in terms of visibility, accessibility, and usability? These are some questions to be answered now by the presentation of Babis.
So, hello everyone. I'm happy to be here with you presenting today. My name is Babis Hatzidiakos. I have a master studies in geoinformatics, and the last years I'm part of the atmospheric physics and chemistry group here in National Observatory of Athens, Greece. So a quite big part of my work here is to access, process, store and visualize atmospheric in situ data, especially from a network that we have developed, maintain, and improve daily here in the National Observatory of Athens, the airquality.gr monitoring network. So in the next few minutes, I'm going to walk you through the practical steps I followed in order to make those in situ data that I access and I manipulate every day in a path to more fair data. And by fair, we mean findable, accessible, interoperable, and reusable. So also at this point, I would like to mention that the work I present focuses on air quality GR data collected from the low-cost PM2.5 sensor as a part of the overall monitoring network that we have operating since 2019. But beyond just showcasing this case study, my goal is to provide here a presentation that a concrete replicable approach that one can be applied directly to other projects, to data that are provided by other projects. And specifically, CiROCCO is a project that provides similar data with the one that I will present right now. So you can see this whole approach as a mirroring to what we can do, what another person can do with the data that coming from this project. So I'll start briefly with an introduction about in-situ data and what is in-situ data. So we can say that it's local on-site or on-position observation data. In-situ data typically gathered using sensor or instruments directly in the field. Data collected from the ground, from the sea, airborne sensors. And this approach provides high resolution, provides accuracy, and very important that it provides localized data that we might missing sometimes by satellite data, by in general remote sensing data. We're missing the small local features that in-situ data can provide us in order to enrich our data, to calibrate our data. So generally, we can say that there are two big categories of in-situ data: geospatial reference data, and by that we mean and the observation data. Since historically in-situ measurements mostly come from static local sensors such as thermometer, anemometer, etc. So this is observation directly on the ground, and there are also in the recent years emerged via dynamic and mobile sensor in the general scope of Internet of Things and crowdsourcing, including the citizen science. So we have physical observations that share a common concept of geolocation. So latitude, longitude, elevation for those data are present in the data sets. And I already mentioned the importance of those data. They are vital for actually providing accurate data that can be used to develop, train, and improve algorithms, but also running models and acquiring information that are not accessible sometimes from space, because we all know that satellites are excellent to provide a large-scale coverage, consistent also, but at some point there might be some limitations. The very small local features that as I mentioned before, and also some obstructed views, etc. We all have faced those problems. So producing, enriching, and calibrating data, in-situ data can be in a high importance of this. So before going to the most practical part of what I did, I want to say a few things about the data that I'm working with. So you can see the QR code in the right-hand side of the airquality.gr website that we have developed, which the monitoring network consists of more than 200 operating low-cost sensors right now. It's a network that is operating since 2019 across and all over Greece in different areas with different characteristics. So we have sensors like the one I have at the bottom left of the slide that provides us with PM 2.5 time series hourly measurements, and we display them in real time via our website in order to the public to be aware of the atmospheric situation in their area. So another thing is that the data that I'm using, and in general we provide from airquality.gr, is calibrated against the reference grade instruments, the super site of the National Observatory in Athens, in-situ, which I mentioned because it's the same super site that we use to calibrate low-cost sensors and low-cost sensors data that come from CiROCCO. So it's the same site, it's in-situ in Athens. We use the same instruments. And in general, I want to mention again that what I'll show now, the tools and the methodology is not limited to airquality.gr, but it's like a mirroring of the data that can be provided, that can be produced by CiROCCO project. Both project deals with similar atmospheric data. PM 2.5 is a pollutant that is familiar with many of us, and we have seen a lot of times. It's not something new or something that we do only in air quality. And also CSV-based and Excel raw formats is something that we face a lot. So both project and many other projects might share the need for better data management and dissemination practices. So to be more to show what I already tell, what we're doing now in order to acquire, analyze airquality.gr data. So we have a functionality that you can click on the map and compare and display the data for a few weeks, for a few days, and compare the different sensors. And we also create a new functionality for internal use in order, a tool that allows us to download data for each one of our sensors. But as I already tell you, we have like more than 200 sensors operating right now. And if we count from 2019, but we might have data from more than 300 or even more sensors. So, for example, if I want to make an analysis or a research to the whole Attica region for a few years, I might need to manipulate more than 40 CSVs or Excels. And you understand that makes things a bit more complicated. And also, it's the advantage of the approach we will try to reach now. So the bigger the data it becomes, not only the worse is the use of many CSVs, but the better is the use of other formats that are designed for specifically these purposes. So as I already tell, I spoke about in-situ data. I show you the data that I'm working with and the problems that we might facing right now. So what is FAIR? What is GEO FAIR principles that is all about? So in general, we can say that despite the importance that we mentioned of in-situ data, finding, accessing, and manipulating in-situ measurements can be difficult or even impossible at some points. Many data are lost, many data are stored only in local laptops, only in local databases. Or there is also the example of data being online, but you cannot find them by a simple search. And the most common for me, I think, is to have the data online, find or manage a way with direct links or other way to access the data actually, but then you cannot easily integrate them with your data set. You cannot easily integrate them with your tools. And this, I think the I and the R of the fairness is a bit connected, because if the data are not reusable, if the data are not well descripted, then it's difficult to incorporate it, to integrate it to your approaches. So we go. I won't tell a bit about the history of FAIR, but there are GEO have implemented other principles before and build upon them, and we resolve to the findable, accessible, interoperable, and reusable principles. So we go one by one to see in our case study, airquality.gr, how what is our goal and what actions we will take in order to reach this goal and to go to a more fairness approach. So, and also need to mention that such approaches have been conducted successfully with satellite-based data a lot, but they are missing. Very few have been implemented with in-situ measurements. So I start with findability. So the goal is very simple: to make air quality data easily searchable. Someone should search online for the PM2.5 measurements, in-situ measurements in Athens, and can easily find the information that needed. So the main action here we choose is to encode data from various sensors into normalized netcdf files. NetCDF, for those who are not familiar, stands for Network Common Data Form, and it is a file format and a library used for storing and accessing multidimensional scientific data. Also designed for array data, as I show you, work with CSVs. When I access data programmatically, I use pandas and the libraries like pandas and GeoPandas with Python. So we have array-oriented data. So we need to transform our data to single to limit the many CSVs to netcdf files. And beyond that, we also need our netcdf to be well structured and the metadata to be present in order our dataset to be self-descriptive and easy to discover online. So we try to enrich the metadata by using the climate and forecast CF from our own. I will refer to this as CF conversions. And finally, we try to touch another field, semantic search. I won't stay here a lot because we have a limitation of time, but briefly, semantic searches go from the traditional search when we use exactly keywords. And if you try to find air pollution in Athens, you might miss a data set that is named PM2.5 pollutant in Athens because you miss the relevant content. You just using different terms and you get only the exact keywords. Then we go to semantic search and we try to reach that as well, to add that as well to our dataset. in order, for example, if someone types how are cardiovascular diseases in Athens affected by air pollution, can find a data set that have PM 2.5, because this whole concept is to find related content and not to match keywords. So I will continue with A, accessibility. So we need to ensure that someone can find the data sets, our data online, and access them easily using the simple protocols and download them easily. So I will upload my final netcdf files to an open access repository. We will explore for future steps more places that should hold those data. So I keep going with I and interoperability. We need to ensure that someone can take those data if he's working with Panoply to visualize, if he's working with Python, if he's working with other GIS software, he can take the netcdf and add it to his work, add our data set to his tools without losing a lot of time or without putting a lot of effort. And something that enhance the interoperability internal at least is that now if a colleague of mine asks me data about 3, 5, or 100 stations, I will send him the same amount of CSVs, but now we try to have only one file that contains a lot of sensors. So this will enhance the whole process of data management and sharing. Finally, reusability. This is also the netcdf format that I mentioned before. We try to end up with a self-descripted multi-dimensional data binary format. Along the metadata, we try to follow these CF conventions, and our variables should have standardized names that have been defined by standard GEO practices, and global attributes should follow the attribute conversion for data discovery. This is also help for someone to take the data set, understand it, and use it as he might want. So this is the overall schema of our workflow. To be more precise, here I work only with 3 sensors here in Athens. To save time, I use data from 3 sensors, but possibly in the future we can try this with way more data, with way more sensors. So for now, I use Glyphad, Athesio, and Kerachini. It's 3 sites that we have here in airquality.gr. And I take those data and I try to encode to an HDF based on the overall principles I already mentioned. And here comes the Lib in-situ library, which is, I can tell that the work that has been done by Lib in-situ team is the thing that inspired us to go to an approach with more fairness of data. It's an open source Python library, for those who don't know, to allows you to transform time series of in-situ measurements. They designed it for solar data, but it's solar in-situ data, so we find similarities with our data. So it's a library, it's open, and provides many tools and CLI commands that help us, provide schemas that help us go from our raw CSV time series to a more well-structured netcdf file. So the final goal is this netcdf file, which contains the data and then reads metadata to upload it to as a nodo. We create as a node of our team, APCG group, and to try to visualize it with different softwares, with different programming languages and libraries, and open it with GIS softwares. So what I explained in the schema is also shown here in this slide. I won't stay long. I just want to say some important points. So our goal is to go from 3 CSV to a single netcdf file that follows some standardized naming and variable naming and global attributes naming. So the input is 3 CSV files. In the workflow, I'll start to inspect the raw files. I prepare those files from conversions and then convert a single sensor to a netcdf. I choose Kerachini sensor to make it a netcdf. and then try to add 2 more sensors to a single NetCDF and see if this actually works in terms of interoperability, and if I can open it with different softwares, and finally to upload it in order to make it accessible online. So exploring the input data, I told you we work a lot with CSVs. This is a sample of a CSV of Keratsini station. You can see that contains a lot of lines of metadata, 17 lines of metadata that explain the station, and then the actual data starts from line 20. Then in order to make our life easier, but it's not necessary to do, we separate this in 2 different files, Keratsini metadata CSV and Keratsini CSV, which contains the actual PM2.5 values. And then here is to define the data model for NetCDF. We can play around with dimensions, with variables, with global attributes. And for that, we're gonna use a lot some custom schemas, and we use possibilities from the in-situ Python library. So a very important thing to mention that in terms of following, not just making a NetCDF file, but making a well-descripted and a correct, let's say, NetCDF file that ensures the integration and the interoperability of other people. We need a well-defined schema, a common data language file, an SDL file that defines the overall structure of our final NetCDF. I will say that our schema should follow, should respect 4 basic rules, and we will see if our NetCDF actually follows this at the end of the presentation. So the metadata should follow the climate and force conventions. There should be a unique time dimension expressed in a specific way. Variables should be standardized based on CF table, and the global attributes should also written in a specific way in order to make our dataset easily citable and discoverable online. So from in-situ provides a custom SDL file for solar data. They have a whole example that shows you how to go from a CSV file to a NetCDF file, and they provide this very helpful SDL file that defines variables and dimension. What I did is to modify it a bit in order to fit my data, to fit atmospheric data, and we end up to air quality schema SDL, which is very similar to what in-situ schema looks like. And in order to give you a short understanding is that the schema has inside some placeholders that helps to write the metadata in a specific way, have standard names, have long names that been human readable, have standard names that have been machine readable in order someone to access programmatically. So if you have a CSV with some headers of your metadata and of your data, then you need to map them with this SDL file to in order to create this well-structured NetCDF file. Shortly, because I mentioned a lot of variables and global attributes, and I said variables should have standardized names according to CF tables, while global attributes must follow some other ACDD attribute conversion data for discovery rules. The basic difference is that variables can be accessed programmatically. They have standard names. So, and the global attributes is used to describe the overall file. I have a table that shows when I recommend and when I say that it's useful to define both. When the presentation will be available online, you can go back and see if you agree and if you find this table useful. I won't stay a lot. I just show you a short example of what standard name and long name meant, how I approach it. So standard name that should follow CF standards is machine readable and standardized. So the obvious example is here that PM2.5 should be written something like mass concentration of PM2.5 ambient aerosol particles in the air. So variable need also a more friendly description, and that's why we have long name. We need to follow those standards. We try to approach it like this. So in our data set, we have a standard name, which is the one you see, this long name for mass concentration of PM2.5. And we have a long name in order to be human readable if someone opens the data sets to understand what he's seeing without prior knowledge. So I said you that we try to match 4 basic rules. So the metadata should be compiled with CF conventions, and I show you here an example in our schema how latitude, how PM2 point value, and all the other variables follow this standard naming, long naming. The units are present, the CRS are present, and we try to match this. Then we have a unique time dimension, but expressed like this in seconds in epoch in UTC. We have the standard variable names. There is a link, a URL that someone can follow to the CF standard name table in order to find what he's looking for. Here for the PM2.5, I choose mass concentration, as I showed you before. And finally, the global attributes. ACDD is, let's say, a list that shows some recommendation of what an HCDF file should have in order to be more discoverable. We try to match most of the fields like title, summary, keywords. We try to include this in a way that our data set is well descripted. So these are the 4 rules. The final file we needed to make the actual conversion is a mapping file. This is also in the example of in-situ. You can find it online. This is something that maps between the CSV and the SDL file I explained before. It can be a JSON or a YAML file in such form. This is the one file that we end up with shortly. So the final and the most important part is to encode actual with a simple CLI command without requiring Python knowledge. This comes also with in-situ, and it helps us encode time series data to NetCDF. So we go from this, having these 4 files for one station, Keratsini, which contains the actual data, Keratsini metadata, the schema that we end up with, and the mapping file. And by running this command, we end up to a Keratsini PM2.5 net NS file. And I wasn't familiar actually with Panoply. I downloaded because I find out that this is the most common software that's used for visualization of NetCDF files. I downloaded when I start trying this practical presentation, this practical example. So I found out that the file I end up with, it was so easy to open, plot the different values in a graph, see that it is geolocated actually, and see that the metadata is written in a way that makes way more sense, at least for me, and I think for people that have worked with similar data sets. So here we have to go from one CSV file to many in the same NetCDF. Things you need to mention in the schema that I mentioned before. Dimension might need to change. I won't say a lot, but I show you briefly that we go from one CSV that have data to Glyphada, GEO, and Keratsini, and then we need to populate our Keratsini metadata to sensors metadata CSV file in order to make this translation. And then by using mapping and the correct SDL, you can do the mapping between the time series, the station, and the metadata. So we end up with combined NC file, which I tried to open also with Panoply, as you see in the left top corner, and I also access it programmatically with Python, and I see that I can easily, using one NS file, plot the data from different sensors. Then I try to share data, to share this file with some of my colleagues that works with GIS softwares, and I find out that it's easy to open. I put here some 2 links for your convenience if you are willing to work with GIS, and you can easily access it and open it with. I checked with 2. The most well-known GIS software is QGIS and ArcGIS, but I assume that it's quite easy and straightforward to do it with other GIS softwares as well. So at this point, I would like to show before and after. So this is the way we improve the interoperability of data for internal use, and we don't have data lost in translation, and we don't have a huge amount of CSVs. This was what we were doing before. We have a data download tool that you can select the sensor location and the exact sensor that you need to download your single CSV. And now we are able to go to something like this, that you can select your data format, and you just can select the region and download an HCDF per region, for example. This is something that we're still working. It's not final. It's just an approach that we think that we can use. So we go from many CSVs to a single HCDF per region, or even per country in some cases. Finally, we create and we upload this final file to as a Zenodo, APCG Zenodo, which provides also a DOI, and it is in order to make it accessible online. For the future steps, we know we need to upload it to more data catalogs, or as is before already mentioned, the Knowledge Hub. We know that there are other catalogs online that might be useful to explore. Also, we are planning to upload a manual of our approach, the data set and the actual steps, the practical steps, step by step, to go from your in-situ atmospheric data to an HDF file in APCG knowledge-based GitHub account. And regarding findability, I thought about the thing that I mentioned before, semantic sets, that I didn't touch a lot in this approach because I face some limitations and some difficulties, but this is something that I will mention also in more details in the manual. We think about adding user stories because those data that I used and the data of CiROCCO will be used in many case studies. They might be used for academic research, from papers, academic work. So it's good to add semantics maybe to our file in order to make sure that we link the different academic or the different case studies with our data sets. So that is from me. Thank you for your time.
I think that is all from us. We can say goodbye for now. Thank you very much.